In this lecture, we're going to deal with how the tachyon monster get excised from string theory. And in the last lecture, what we found was that things like the electron, in addition to having properties that you might think of as ordinary, have a number of remarkable properties associated with them, things that you mostly don't hear about when you take a science course. For example, you'll recall that an electron behaves like a spinner. That was the object that you can think of it as an arrow, but if you walk around it any even number of times, the arrow's pointing at you, but if you walk around it any odd number of times, it's pointed away. That's one very strange property. We don't see things in the world around us showing this kind of behavior. The other strange thing that we saw in the last lecture is a funny kind of property with respect to two electrons. If you have sort of two electrons in one order and you switch the order and try to measure some property of the pair, you find out that the first answer gives you something which is minus the answer you get from the second order. That's called anti-commutativity, is the word that mathematicians use for that property. And electrons are examples of real objects that exhibit the behavior of anti-commutativity. It is the source of the Pauli exclusion principle and all of chemistry. So it's a very strange mixture of mathematics and observation. In 1977, three physicists, Gliazzi, Shirk, and Olive, observed that it is supersymmetry, the equality of bosons and fermions, that kills the tachyon monster. So we want to explore this idea of, well, first of all, what is symmetry? We have talked about symmetry in previous lectures with regard to the Pythagorean theorem. We want to come back to this because it turns out that the notion of symmetry is probably the most fundamental thing we use in areas like string theory and in much of fundamental physics. So we want to know what is symmetry, and then we want to know what's so super about supersymmetry. So we're going to turn to a discussion of what we mean by the super part of supersymmetry. Let's begin with our discussion of symmetry. In our world, and in the everyday world, if you walk around and talk to your friends about symmetry, they would probably tell you something like, well, let me show you a model. That, I suspect, looks symmetrical. That doesn't, right? Because our sense of symmetry is often a sense of balance. So having arms like this, or somehow there's an equal weight to both sides, that is somehow more aesthetically pleasing to us than to see a figure that looks like this. So that's what symmetry means in the everyday realm. But when a mathematician or a physicist uses the word symmetry, that's not what we're actually talking about. Now, in order to talk about symmetry, once again, we're going to imagine a problem, which I've returned to several different times, namely the problem of covering this stage with a carpet. This time we're going to imagine that the stage is squares. Previous discussions I've considered rectangles. This time it suffices to consider a square. So the length along the front of the stage will be the same as the length along the side, and we'll choose both of these numbers to, say, be 5 inches, imagining that I can shrink the stage at will, something that with mathematics I can do. Then the area of the stage will clearly be the length along the front times the length along the side. If I say the front end is 5 inches and the side is 5 inches, then the area of the stage is 25 square inches. So where's this thing called symmetry lurking? Well, we're going to learn about symmetry in the form of a little game. Imagine that there was a mischievous gnome, and we'll name the gnome Tachyon, after that monster that we've been worried about so often. So let's say that this gnome named Tachyon appears, and he informs me he wishes to play a game. Now, the game is very simple. He says that he can make me wealthy beyond my dreams if I'll answer a question 4 times correctly. And what the question is suppose he gives you the area of the stage, and he has magical powers And he tells you with his magical powers, he can actually change any length into minus itself. Well, it can't happen in our world, but since this is a fantasy, let's go ahead and consider it. But he does this randomly. Sometimes he does it, sometimes he doesn't. So, he's going to ask you 4 times, when did he do this? Well, let's see, how does this work? If it's 5 times 5, that's 25 square inches. If it's 5 minus 5 times minus 5, that's also 25 square inches. So there's no way for you to tell when he used his powers. Did he use his powers or not? You can't tell. And the reason you cannot tell is what a scientist or mathematician refers to as asymmetry. In this example, if you take the 2 lengths, which are 5 times 5, you get 25 square inches. Or if you replace the 5 by a minus 5 in both places, you get minus 5 times minus 5, that's 25 square inches also. So this is an example of what a mathematician or a physicist means by the word symmetry. We mean the replacement of some number or possibly algebraic variable by a different algebraic variable, and still it gives us the same answer. So it's not a fair game. So physicists like to use formal expressions. We say that the symmetry of the area has an invariance with respect to the transformation that sends one length and the other length into minus themselves. Very fancy language, very simple idea, I hope. Now, instead of using sentences, we physicists actually write equations. And so, let me use the letter P for the tachyon's name, and let's try to write equations that describe his powers. Well, the front length is 5 inches. When tachyon uses his power, he changes that number to minus 5. On the other hand, when he does this, since he has to do it on both sides, if he takes the area of the stage and uses his power, there's no change at all. So this power that we're talking about can be written as an equation, and on my transparency, I've actually indicated it. When we apply this power to the area, we get the same answer. When we apply it to the lengths of the edge, we get minus the answer. So we can think of his power as being the power to exchange ordinary numbers into negative numbers. Now, so we tell Tachyon the game is not fair. He decides to disappear, and of course we don't get all the money that's far beyond our dreams. But Tachyon might be persistent. And so he comes back another day and wants to play a relatively similar game. Now, in the first game, it was kind of simple. What he did was he said, well, I'm going to change numbers into minus themselves. This time, he decides to play the game not with the surface area of the stage, but with a triangle. And in fact, we've visited the triangle several times, so let's go back once more because it's a useful device in our thinking about these things. So there is we can think of it as our ladder in the case of the wall, but let's just look at this and lift one side. And there we see our right triangle described. Okay, so now Tachyon is going to have a new game. Now we have learned, of course, that the area of the green is equal to the area of the brown plus the area of the blue. And now Tachyon says, look, I'll give you wealth beyond your dreams if I give you the size of the green area, and then you simply have to guess the size of the blue and the size of the brown. So that's the game. If you get it correct, I'll make you wealthy beyond your dreams. But there's only one little problem with this game. Once again, there's a symmetry here. You see, in the case where, in fact, let's look at the house because we can see an example of our house a little bit more clearly. So here's our house once again, and there's our ladder laying on the side. It has a length. There it is. And we can grow our 2 squares. There they are once again. Now, when Tachyon decides to play his game, it's like lifting the ladder like this. And he will give us the number that represents the area of the green square, but he wants us to guess what are the brown and the blue square areas. But there's no way for us to do that because we can look at it like this, where for example, let's lay it flat. Then there's only the blue square. There's no brown square at all. Or we could lay it on the side where there's only a brown square, but no blue square at all. And so there's no way for us to guess which of these two things tachyon is actually used. Now, in this case, it's actually very interesting that it's very different from our other example. In our other example, all tachyon could do was change a number into minus itself. In this example, tachyon has the ability to change the orientation of the ladder, and when he does so, there's no way for us to tell because the only thing we know is the area of the green square. So we don't know if the green square, if the ladder's in the vertical position, because that area is the same, or we don't know if the ladder is oriented like that. It's still the same area. And so once again, this is a problem with a symmetry. The symmetry here, however, is very different. You see, you can cause a little bit of mixture, like we see there. So we have a brown and a blue, or we can cause more mixture, a brown and a blue, or we can go totally to brown, and every single one of those has the property that the green is equal to the sum of the other two. Sometimes one of the other ones is not there. So this kind of symmetry is what we physicists call a continuous symmetry, meaning you can change it from one to the other in small steps or in large steps. Now, this notion of continuous symmetry turns out to be one of the critical things in nature. And we can write equations that accomplish these changes. These are done with what we physicists, mathematicians call these things generators. We can also call them exchangers because mentally that's all they do is they exchange. It's like exchanging the blue and the brown squares back and forth, and no one can tell the difference if you've done that switch because the area of the green is always the sum of the two. So if you exchange the two squares, who can tell? But in the case where you can change by a little bit, then we have this additional complication. We have to tell tachyon to go because he's asking us to answer questions where there is a symmetry. And the symmetry makes it impossible for us to know when tachyon has used his powers or not. Now let me discuss this notion of supersymmetry a bit. We're used to the idea at this point in the lecture that there are two different distinct classes of objects in the universe in which we live. We can see these objects on a transparency that I'll bring up here. We can see them first in terms of stuff that makes up us. That's the stuff that makes up us. Namely, we are mostly up and down quarks, because those are our protons and neutrons. Our atoms have electrons that whirl about them, and so these are the basic building blocks for us. On the other hand, to hold those building blocks in place require forces, and we can assemble the four forces with their carriers next to the stuff that makes up us. There's the graviton, large G. There is the Higgs particle, which we now think is responsible for mass. There are the W and Z particles, which are one form of nuclear energy. There are the gluons, which were the other form of nuclear energy we talked about. And then there was a photon, the force carrier for light. All of the stuff that is either red or blue is fermion. All the stuff that's green is boson. Now, let's imagine tachyon had the power to come into our world. And instead of exchanging things that we know, because remember, red and blue fermion, green boson, let's imagine that tachyon has this peculiar property that he can take an object like the electron and only change its rate of spin. None of its other characteristics, not its charge, not its mass, only its rate of spin. And similarly, he can do this not just for the electron, but for all of the ordinary matter that we know. So that's what we're going to imagine about tachyon. If that's the case, if you change the spin of an electron, it's no longer an electron, because the spin is part of the reason why chemistry works. So if you remove the spin, then chemistry doesn't work. So you get something that's not an electron. And in fact, if tachyon uses his nefarious powers to their complete extent, what you can imagine is that for every particle in our world, tachyon uses his exchange ability to replace it by something that differs by 1/2 a unit of spin. So, for example, in our world, we have up quarks and down quarks that sit inside of protons. If tachyon uses his amazing powers, then he can replace those by objects that instead of spinning at the rate of spin 1/2, spin at rate 0. In our world, we have the carrier for the force, for the electromagnetic force, the so-called photon. Tachyon uses his magical powers. Our photon spins at rate 1. Tachyon can change the spin rate so that it becomes spin 1/2. Well, if it becomes spin 1/2, then it's no longer a photon that we know. Again, in our world, we have electrons. Tachyon can use his power to replace this by an object that spins at rate 0. Our electron spins at rate 1/2. So, if tachyon's powers were actually real, roughly speaking, he could double the amount of stuff that makes up reality. Everything on the left-hand side of this transparency is where we find the physics of our universe. It's where we visited when we went to the world of the quantum. We met the quantum denizens. Everything on the right side of this diagram has never been seen in the laboratory. Now, what does this have to do with string theory? Well, remember, the banishment of the tachyon required that you had equal numbers of fermions and bosons in order to interact with the tachyon, and then you can use the minus sign that are associated with the fermions. So, this image of an imagined universe that we've described here would be exactly the kind of mathematical structure you would need in order to get rid of the tachyon, the real tachyon, the mathematical tachyon from string theory. So, this balance is what we mean by supersymmetry. Instead of interchanging blue and brown squares, we interchange the spins of particles. In our world, the graviton is spin 2. Under tachyon's magical powers, there's something that looks almost like a graviton, but its spin rate is spin 3/2. It is always that we either add 1/2 a unit of spin or we subtract 1/2 a unit of spin. When we do that, we are then in position to find out that we can cancel the effect of the mathematical tachyon that's threatening to destroy string theory. So that's the magic of the so-called supersymmetry. And the concept of supersymmetry itself is actually very new in physics. It only appeared, that is, people only began to consider models where you had this balance in the late 1960s in Russia and the early 70s in Europe and the United States. So the idea itself is, roughly speaking, just over 35 years old, or perhaps 40 if we do some counting in a different way. So it's a very new idea about the way our universe might be put together. Now, I have a personal note on this point because, you see, supersymmetry is in fact the first subject that drew me into theoretical physics. I was a graduate student at MIT. One day I read a research paper. In this paper there appeared mathematics, the likes of which I had never seen before. And in fact, it was so fascinating to me that I began to ask my faculty advisor if he knew anything about this new idea. It turned out he didn't. But the thing that was so remarkable and surprising is that nobody in my department knew anything about this idea. So I was a young graduate student who wanted to study this, and therefore I was forced to turn to the research literature. This idea of balance, for me, personally as a physicist, is something that so deeply sort of felt that it drove my entire direction in the field. And this is how physicists work. Although we often talk about the logic that drives us, at some level there's a kind of irrationality. There's a regard for what we think of as beauty that seems to play an important role. Now, of course, that cannot be the end of science. It cannot be that our intuition, our sense of beauty, is totally what drives science. And in fact, it's not. It has to be the case that when we write these equations which have these kinds of beautiful ideas in them, beautiful mathematical ideas, beauty in the sense of mathematics that we discussed in our relationship and understanding music to mathematics, that beauty is never typically sufficient to describe physics. We always, at the end of the day, have to return to experiment. Nonetheless, it has been our experience that whenever we find the right answer, we can typically find evidence of this beauty. Let me talk a little bit more about supersymmetry, this kind of strange balance idea, because you see, supersymmetry is both child and parent in string theory. Well, what do I mean by that? Well, in the original bosonic string that had the tachyon, which we've been bedeviled with throughout most of our lectures in recent times, no one knew about the idea of supersymmetry. It came because of the banishment of the tachyon. So this kind of figure that we can see here is a result of string theory. However, if you'll remember, even once you introduce the idea of spin, that's not sufficient to get a string theory where you banish the tachyon. You have to have not only just objects that spin at different rates by 1/2 a unit, but they have to be coming in equal numbers. So supersymmetry was born from string theory, at least the need to make string theory consistent. In a future lesson, we are going to talk about a next generation of string. We've talked about the superstring to some degree, but at a future lecture, we will return to the notion of superstring. In fact, we're going to find out that there are 5 of them, remarkably enough. That's, of course, an embarrassment of riches, and at the end of the day, it's all related to these kinds of balance properties that we're talking about in terms of supersymmetry. Well, supersymmetry is such a strange idea that it turns out that it actually doesn't require strings. We can abstract the mathematics of this beautiful balance and just ask a simple question. Everything on the left-hand side of this table exists in a piece of mathematical physics called the Standard Model. The Standard Model is supported literally by tens of thousands of experiments. So, if we have such a description, such a precise description of nature, let's just make it balance. Let's just change the equations so they actually exhibit this balance. We know how to do that. When we do that, we get theories that are called supersymmetry. And in particular, this leads from the Standard Model to what is called the minimal supersymmetric Standard Model. Again, in a future lecture, we're going to find out what's special about this model, but the idea is this picture doesn't entail string theory at all. It's just supersymmetry. Now, remember the sequence of logic was supersymmetry was implied by string theory. But once you understand what supersymmetry is, you can ask, can it exist without string theory? And the answer is yes, it can. And so this is going to lead the physics community in a little bit of a conundrum, because you see, in a few years, at the Large Hadron Collider, the LHC, people are going to be looking for evidence of supersymmetry. They're going to look to see whether we can find the kind of evidence that shows us that the objects on the right-hand side of this diagram actually exist in nature. Now let's, for the sake of argument, assume that the answer is yes. We find these superpartners. For persons such as myself, who have spent their essentially entire theoretical physics career wondering about these things, this of course would be a source of great joy. It will mean that our sense of aesthetics has not led us astray in understanding nature. But will it prove string theory is correct? The unfortunate answer is no, because supersymmetry can actually exist without string theory. What is it that string theory adds to this picture? It's all of the extra vibrations. Remember, a string is like a musical instrument. These are like single notes of a musical instrument. So in order for string theory to work, yes, we want to be able to produce these notes, but the string should be able to produce more notes in addition to this. So string theory will get a boost if we see supersymmetry, but it won't be a definitive answer. I mentioned a moment ago the 5 different strings. Let me say a few more words about them right now, and we'll return to them again because they're going to be leading us to even greater structure. And by the way, let me also say that the reason we physicists keep finding these larger and larger structures is because at each stage there's something left undone, and we're trying to get it all done in a single coherent picture, and that will be our final destination, superstring M theory. Let's talk about the superstrings. In fact, I mentioned there were 5, and we will study them, but let me try to give you a sense of where this number 5 comes from. You remember in a previous lecture, I showed you a picture of an organ pipe, and I said that in some sense, the organ pipe captures the mathematics of string theory. We could have an organ pipe where both ends were open, or we could have an organ pipe where both ends are closed. And both kinds of organ pipes can actually make notes. You can go and find an organ and actually verify this. Now, the mathematics of superstrings is like that. So, it also, however, so that means right offhand, you immediately realize there should be 2 superstrings. Open organ pipes, closed organ pipes. So that gives us 2 of the 5. However, we can also do something more interesting. We have talked about the fact that the electron behaves in this very funny way where in walking around it, it acts as though it's flipping its direction. That's a spinner. And the superstrings are all defined by spinners. And so what you can, in addition, ask is, how many spinners do I add? So we've got open and close for the ends. And then the question is, how many of these spinners do I add? Well, you can add 1. That's the simplest extension. And if you do that, you get what's called the type 1 closed superstring. Or you can add 2. Well, if you add 2, then it turns out that there are 2 ways to do it. You can add 2 left-handed spinners, or you can add 1 left-handed or 1 right-handed, or you could add 2 right-handed spinners. Well, it turns out that the mathematics of 2 right-handed spinners is exactly the same as the mathematics of 2 left-handed spinners. And so that just gives us 2 more varieties. And so by these very relatively simple arguments, we come to understand that there must be at least 4 of these things called superstrings. Well, I promised you 5. And yet I haven't delivered on that promise. The 5th superstring is a most remarkable object. And we're going to spend an entire lecture talking about this 5th superstring. It was invented in 1984 at Princeton. It's called the heterotic string. David Gross, Emil Martinek, Ryan Rohm, and Jeff Harvey were the people who wrote the mathematics describing this object. In some ways, it can be thought of as a superposition of things we have already seen. Remember, we started with the old bosonic string with its 25 spatial directions, and then we found that when we add spin to it, there's a new kind of string, the so-called superstring, that only has 9 spatial directions. Suppose there was some way to glue these 2 things together and get some kind of consistent mathematics. Well, one question would be in how many number of dimensions? Because one piece says 25 spatial directions, the other says 9 spatial directions. What's the right answer? These are going to be the challenges that we're going to face with the heterotic string. When we confront this challenge, however, there's a wonderful reward that we're going to receive. Einstein's dream of a unified field theory becomes obviously solved with the construction of the heterotic string. So this last one we can think of as being the direct answer to Einstein's question, and that's the one we're going to spend some special detail and time investigating in the future.